Okay, good afternoon. My name is Marc, and I'm here to give an overview of our work at super resolution for overhead imagery. This is a work done with my colleagues at the Applied Physics Lab at Johns Hopkins University. So following recent trends on this area, we developed a single image super resolution framework using neural nets for both satellite and airborne imagery. We set the problem as a learning task where we show the network low resolution and high resolution pairs of the same image, and we hope that the network will learn that mapping between the low and the high res so that it can recover all the pixels and the information lost in the acquisition process. So this in airborne imagery and overhead imagery has profound implications. Imagine if you have an image with a ground sampling distance of 4 meters, for instance, and you just were to apply a super resolution algorithm that can do a 4x enhancement. You, in essence, have an image of a virtual GSD of 1 meter. And that has implications on improved capabilities downstream in terms of object detection, semantic segmentation. So it becomes a task of estimating plausible information and recovering semantics in the scene. So our super resolution framework uses the recently proposed densely connected blocks, and we fit it into a GAN framework where we add a secondary network, the discriminator. That's how it's known in the world of GANs. And the goal of the discriminator is basically determine whether that image that is generated by our super res network is realistic or it can definitely be improved. And as training progresses, the generator or our super res network goal is to get better and better at producing a more realistic version of the image, and the discriminator needs to spot when that is a generated image, not a real one. So going into a bit of the details, as I said earlier, we've created a super res network, a generator, using the dense blocks. Those are like blocks that basically concatenate feature maps and expose lower layer feature maps throughout the network. In between each of these dense blocks, what we add is we added a layer that, in essence, produces a 2x upsample of the feature map and creating a sort of a pyramidal approach. And that allows us to, as the image progresses through the network, to recover finer and finer details as it goes along. In the case of the discriminator during training, we've just used a very classic architecture where we extract features and then we perform binary classification to just say whether that image is a generated one or it's an actual image. Also, besides exploring different types of architectures, we've also experimented with the loss type. We have a combination of different losses, the adversarial loss, the content loss, which tries to encourage the output pixels of the generated image to sort of match the target image. And also we've experimented with a feature loss, which in essence tries to determine how similar the feature representation of the output of the super res network and the actual target look. Ultimately, we saw that the feature loss had the least impact. We believe that it's because the pre-trained model that we used was trained on data that it looks very different from the actual data from overhead in terms of scale, viewpoint, and geometry. So here are some results of the approach for different types of images and multi-bands and panchromatic bands for different factors of resolution increase. And what we also done to put it in context, we've applied the same methods to our more known data sets like the phase data set, and also, as I said earlier, these algorithms can have implications on capabilities for other algorithms. In case of the phase detection or the object tracking, we have an aerial video that actually the original input, the tracker loses the actual person, but when applying the super res, it is actually able to continue with tracking the person. So that's it. Thank you, and I'll see you in the poster session.